disappear.
안녕하십니까. 금일 퓨처 브레이크 시스템인 EMB에 대한 온라인 세션의 진행을 맡게 된 HL만도 브레이크 R&D 시스템실의 최욱진 상무입니다. 온라인 세션을 진행하기에 앞서 23 CES의 만도 최초 전시 참여 행사의 일환인 본 행사에 참여해 주신 국내 기업, 학교, 연구기관 참석자 여러분들께 감사의 인사를 드리며 새롭게 시작하는 2023년 새해에 복 많이 받으십시오. 금일 진행하게 되는 퓨처 브레이크 시스템 세션은 자율주행 차량의 브레이크 바이어 와이어 시스템인 EMB 제품에 대한 HL만도가 추진하고 있는 기술 사항에 대해 설명드리는 자리가 되겠으며 향후 미래 브레이크 시스템인 EMB가 어떤 철학과 의미를 두고 개발되고 있는지에 대한 이해를 하시는데 조금이라도 도움이 될 수 있도록 준비하여 보았습니다. 본 행사의 순서는 HL만도의 CEO이신 조성현 사장님의 오프닝으로부터 4가지 토픽에 대한 기술 세션이 순차적으로 진행될 예정입니다. 발표 시간은 약 40분 내외이며 모든 세션은 영어로 진행될 예정이니 참고하시기 바랍니다. 모든 세션이 완료된 후 별도의 Q&A 시간이 20여 분간 진행될 예정이며 질문을 하시려는 참석자분은 보시는 화면 우측 상단 질문란에 입력하시면 되겠습니다. 시간 내에 답변드리지 못하는 질문에 대해서는 세션이 완료된 후 질문자 분들께 별도의 메일을 통해 답변 드릴 수 있도록 하겠습니다. 지금부터 본 행사의 맨 처음 순서인 HL만도의 CEO이신 조성현 사장님의 오프닝 멘트로 세션을 시작하도록 하겠습니다.
Good morning and good afternoon to the audience joining us online from around the world. This is Steve Cho, CEO of HLmando. I'd like to thank everyone who joined this online conference to hear and share great ideas and innovation about future mobility technology, especially in the area of motion control. As many of you already know, HLmando specializes in xEV and autonomous driving solutions, including brake, steering, suspension, drive and traction, and power electronics for light vehicles, as well as different types of mobility, including micro-mobility, robots, and more. HLmando has been in the vehicle chassis business for more than 60 years. During that time, working together closely with many OEMs globally through shared experiences and expertise. We have built a strong foundation to enable our mutual success. As the industry and technology continue to dramatically change, we have been closely collaborating with our customers and partners to transform vehicles to mobility that is electrified and autonomous. Imagine every move. That is what HLmando ultimately envisions, and that is the key message for CES 2023. With HL's technology, every move you or the world make can and will be safer, greener, and easier. Today, our speakers will share their valuable expertise and insights on the future of brake system, which is electromechanical brake system. I hope this conference will trigger your imagination and innovation. Thank you very much.
지금까지 조성현 사장님의 말씀이 있으셨습니다. 이후 기술 세션은 4가지 기술 세션으로 이어질 예정인데, 첫 번째 세션은 EMB Why Now라고 하는 시장 요구에 대한 세션으로 세션으로 시작해서, 두 번째 세션은 Vehicle Electrical Architecture Supporting EMB, 세 번째는 Advantages of Digital Twins for Future Development of Safety, 마지막으로는 Advantages and Challenge for EMB Control의 4가지 세션으로 구성되었으며, 기술 내용은 하드웨어부터 소프트웨어까지 기술을 모두 다루는 내용으로 준비되었으니 관심을 가지고 시청하여 주시면 감사하겠습니다. 지금부터 기술 세션을 보시겠습니다.
Hello, my name is Jeff Pontius. I'm the Director of Brake Engineering here at HL Mando. Today, we're going to talk about electromechanical brakes, and specifically, I'd like to start with what is EMB. EMB, or electromechanical brake, is the next step forward in technology and braking systems and components. Working in cooperation, HL Mando with HL Mechatronics have designed an electromechanical brake that is a fully dry brake caliper. HL Mando's EMB design utilizes proven technology from within HL Mando's brake and steering products' core technologies, and can be utilized as either a 2-channel or 4-channel configuration, depending on the customer's specific application. Utilizing a brushless motor and an onboard ECU, individual wheel end control is possible. Either full ABS ESC at the wheel end or first slip mitigation and handoff to a centralized domain controller is possible. Under development for 3 years, the design has successfully completed a full bench and dynamometer DV, along with thousands of miles of on-vehicle development. The first analog brake systems were introduced in the 1930s, but were not 100% installed to vehicles in the USA until legislation enacted in 2007 required their inclusion. Today, even with the widespread availability of vacuumless boost technology, such as Mando's IDB line of products, which combine the functions of the traditional booster, master cylinder, and ABS ESC control module into a one-box solution, some automakers have not yet introduced this technology. This is to say that sometimes technology is slow to be introduced in brake systems. Furthermore, there have been numerous past attempts by brake component manufacturers to introduce new brake concepts, including electromechanical brakes. So one may wonder or ask the question, why now? There are 2 main topics I will touch on regarding why now is the right time for EMBs. The first are the enablers, and the second are the advantages. There are several key market shifts at a vehicle level that enable the introduction of EMB at this time. The main market shift is the electrification of the vehicle powertrain. As we know, multiple car manufacturers have already made pledges to convert their entire vehicle lineup from ICE to BEV vehicles in the next decade. Others have pledged conversion of a high percentage of their vehicles to BEV or alternative fuels within a similar timeframe. This trend is easily observed, with several significant BEV vehicle launches having already occurred and dozens, if not hundreds, of others under development within car manufacturers globally. A second major change is the introduction of new technology for other safety-critical automotive components, such as electrical or steer-by-wire and autonomous driving features. What these 2 market changes have in common is that they combine to lead increased vehicle sophistication and, more specifically, redundancy in the vehicle's electrical architecture. This topic will be discussed in greater detail in a few minutes, but from the safety perspective, the redundancy or the backup or secondary electrical system in the vehicle electrical architecture is the key enabler to EMB introduction at this time. Now, speaking about the advantages. There are many advantages to the HL Mando EMB when compared to a conventional brake system. Some of these advantages will be transparent or not easily recognized by the driver or passenger of the vehicle, but offer other advantages. Some of these advantages are lower brake drag, leading to improved fuel economy or battery mileage, the elimination of brake fluid from the vehicle. This alone has many benefits. Elimination of hydraulic lines from the vehicles. Hydraulic line corrosion has been a problem on some vehicles in the past, and hydraulic connections are known to be a slow manufacturing and high DFMEA failure mode operation. elimination of brake evacuation and fill issues and associated repairs at vehicle assembly, elimination of a caustic and flammable fluid from the vehicle, improved environmental sustainability, elimination or lack of recycling of fluid at repair or end of life, decoupling of the pedal for regenerative and autonomous driving, compact package similar in size to existing MOC calipers, flexibility in parking brake function integration, can be easily applied to two wheels, either the front or the rear, or four wheels, depending on OEM and vehicle needs. Decreased stopping distance due to decreased time to response of electrical systems compared to hydraulic systems. Robust integrated parking brake function, ideal for vehicles with CVTs or with no parking poles. Besides the above items, it is anticipated that there will be new value-added features that HL Mando and customer engineers will be able to take advantage of as EMB is applied to new vehicle platforms.
Hello, my name is Kate Hurtubise, and I'm a system safety engineer at Hala Mechatronics. Hala's EMB system architecture is designed to be implemented with vehicle-level dual power supplies and dual vehicle-level brake control units. The independent power at each controller allows prevention of single-point faults from degrading the system. Each BCU sends commands to all four corners, and the commands are allocated as primary or secondary based on a diagonal split design. Independent EMB controllers are at each corner. In addition to applying the prescribed clamp force, they also are each electronic park brake capable and wheel speed compatible. This redundancy prevents single point faults from multiple systems, from power supply and from vehicle VCU faults. The safety requirements have been implemented from multiple regulatory requirement sources and also in accordance with ISO 26262 specifications. These safety requirements are evaluated according to vehicle-level safety goals from multiple OEMs. Per ISO 26262 specifications, each safety goal is analyzed by deriving a qualitative FTA. In addition to the OEM and regulatory specified requirements, additional safety requirements are identified through this fault tree analysis. These safety requirements are considered at both corner level and vehicle level and traced to the safety goal. Hala is also targeting regulation compliant performance requirements, deceleration metrics for each fail functional configuration of the vehicle. Control strategies have been derived for each variation of fail functional operation as shown below.
Hello, my name is Jeremy Dobbs. I'm a controls engineer at HL Mechatronics in Bay City, Michigan. And today I'm going to be talking about the advantages that digital twin models bring to the development of safety critical components in automotive systems. So just wanted to start by explaining what a digital twin is. So a digital twin is a model of a physical system that emulates important features of it. So basically the key dynamics of the system and software behavior, and is interface compatible with the physical system that it will be integrated into. So in case of our electromechanical brake or EMB, this would include being compatible with the communication bus, electrical power bus, and mechanical interfaces of a virtual vehicle platform that it could be integrated into. So this cross-domain model includes the mechanical, electrical, thermal, and software behavior of the system that we're trying to model, and it allows for a virtualization of functional testing of the system, calibration, and feature development as we're exploring new features that the system could have. So in the case of the automotive industry, when we talk about a digital twin, on the OEM side, this would include a complete vehicle model. So it would include, in many cases, models of the different control units that are in the vehicle that are delivered by tier 1 suppliers. So for example, the brake and steering systems, models of components that are owned by the OEM. So like the powertrain, and then typically a co-simulation with a vehicle dynamics tool like CarSim or CarMaker. Then on the supplier side, so these models that we deliver to the OEM would include a plant model of the system dynamics of the mechanical design, a model of the full software stack of the system, where the fidelity of that software model would be fit to meet the application. So this could go anywhere from all the way down to the embedded registers of the actual microprocessor. So this would be like a virtual ECU model, something higher level earlier in development that would be more like an algorithm level model of the behavior of the system. And then additionally, this model will include the hardware models of the electrical components that are key to the system's behavior. So for example, things like the motor drive circuitry and interfaces with any of the sensors. So why do we want to create digital twins? So the main driving factors are that it reduces development costs and time, because it can decrease the amount of prototype vehicles needed in order to go through a full automotive development cycle. Basically, more and more of your integration testing can be done in a virtual environment, and you can find issues and correct them before they actually get to the vehicle. So it allows us to do virtual trade studies where we can rapidly iterate over different design concepts without having to build up hardware. And it increases the efficiency of the development process, because we're spending less time actually ordering tests or doing tests ourselves, and more time on solving the engineering problems. So it simplifies the root cause analysis of the system. So basically we can find defects in our design earlier in development, preferably before they actually reach the customer. And on the OEM side, they're able to perform integration testing between their different subcomponents earlier in the development cycle. So things like the communication between different electrical components in the vehicle can be tested in a virtual environment before the hardware is actually available. And OEMs are rapidly adopting virtualization requirements for all electrical tier 1 suppliers. So HL Mechatronics has been working with OEM partners to help define this process. We've been in discussions with the OEMs that we work with on what the right process is to follow this, how we can integrate these models through the entire V cycle to ease our development. So, and I just wanted to give an example specifically of how digital twin models can be applied to EMB systems. So this is just showing sort of what the model looks like, where there's a multi-domain simulation of the braking actuator, where there's a calibration file that could be actual calibrations for the brake from the hardware that are loaded into the model, a model of the software, electrical hardware, and mechanical plant that are all interfacing with one another in real time. And then the interfaces basically in and out of the model would include the communications, electrical interfaces, in the case of the EMB, a wheel speed signal, coming from a sensor model. Then the outputs would be the current draw that's going on to the electrical bus so that we can predict basically our power loading, temperatures so that we know where we are thermally with the design, and then the actual clamping force output of the system, since that tells us how we're doing with our performance requirements. So EMB is in a position where it's uniquely suited to take advantage of digital twin development because it's an emerging technology, which means that there is a great need for rapid trade studies and design iteration as the technology advances. So this virtualization is allowing us to keep up with the customer demand for EMB development. So in conclusion, digital twin models are going to be required to meet OEM virtualization requirements. And HL Mechatronics is a leader in this area. We have in-house expertise in the design and modeling of many cross-domain areas. So power electronics, motors and sensors, software, mechanical actuators, mechatronic integration, and just in general steering, brake, and propulsion technology. And digital twin models reduce development costs and time and reduce the need for hardware testing.
Hi, my name is Raja Ravi Ramakrishnan. I am Chief Scientist in the controls area at HALA Mechatronics. So we are responsible for controls development for various products. And what I'm going to talk today is about advantages and challenges for EMB controls. So this slide shows an architecture of a brake-by-wire or EMB system, where you can see that the actuators and the motor is attached to all the four wheels. This kind of architecture for EMB provides a lot of flexibility especially in vehicle controls while stopping and how to maneuver the vehicle. It also gives us another aspect of it is what we call for safety, which is what we call as redundancy, because these actuators are similar and each actuators are placed in different wheels. So it give us a redundant architecture where we have multiple actuators trying to control the vehicle. So from a safety architecture and as well as from a performance perspective, EMB takes a whole new domain of braking architecture for the future automotive. Now, what are the key advantages for EMB control? Why do we have to go for EMB will be the next question, which I'll be trying to answer. The main advantages is, as you see here, increases the safety by decreasing the stopping distance compared with pure electric braking. With EMB, as the motor is reacting, it's much faster compared to a hydraulic system trying to stop the vehicle, and you can actually decrease the stopping distance because of the actuation time and also by improving the amount of force applied to the brakes. The other key aspect of EMB control is the undesirable feedbacks in hydraulics. I think everybody who have driven the hydraulics braking would have seen some undesirable pedal feedbacks while it going through potholes, or whether you're braking too fast, you can see an undesirable feedbacks in hydraulics. In EMB type systems, such feedbacks can be better managed, and a driver experience for a better feedback mechanism can be given. A driver actually can have a better feel of controls of the brakes. So such high level of automation or high level of control of feedback allows this EMB control to be superior compared to what today's hydraulics braking is. The other key technical area where EMB is performing better is the active gap control reduced during drag or brake pad wear, which reduces the brake pad wear. So if you see it, the active gap control reduces due to the active gap control, we can reduce the amount of brake back wear and the drag applied to the pads. And therefore, the maintenance of pad wear and can be adjusted and it can be improved compared to the today's normal hydraulics braking. And especially during an emergency kind of braking, the amount of force we apply tends to be controlled, where EMB can control the accurate amount of force we need to apply, thereby eliminating overstressing or understressing the pad. The other key area is also what we call as better control of all the brakes with respect to the driver's intention. Now, in EMB control architecture, as I showed in the previous slide, you would have seen that the driver intention is actually captured, and we can actually give the right amount of force needed for the brakes so that we can actually maintain the pad wear as well as provide a better control of the brakes. Thereby, his intention can be clearly understood and we can provide the accurate response from a brake perspective. The other final advantage we would see is the driving comfort can be increased by reduced pedal force, especially with different type of drivers and with a different amount of force. We need to provide a better user friendly, where lower pedal force are needed to provide larger braking force. We can adjust that tuning. So that is a key feature when we go into EMB. We can actually adjust the tuning, just like steering is today, where we have different types of tuning, like sports, comfort. We can have different types of tuning pedal force and tunable pedal feel also. So the driver amount of force they need to apply can be tuned, and also how much they are able to feel back can also be adjusted. Such great tunability and experience in EMB provides a huge advantage compared to the hydraulics braking, which we are having today. Now, the advantages clearly seen in the previous slide shows a huge advantage why the market is moving towards EMB and why there's a huge push for this new technology in industry. But is that without any challenge? There are many challenges to overcome. And this slide kind of provides the main challenges we are trying to overcome in this technology. As you know, now that there is no mechanical or physical hydraulic connections between the pedal and the brake, this requires safety, and safety is the key in all of these. This requires, therefore, high redundancy to make sure upon a failure that the system shall be capable to perform. It's a very key point because we don't want one brakes to fail all the brakes and the system is without any braking control. So therefore, redundancy is a key aspect. This requires high fault tolerant communication hardware. The redundancy doesn't just stop by motor. It is in the whole system architecture design when we are doing it. So this requires high fault tolerant communication hardware. Key redundancies, most of the sensors and actuators which are used, that is including the motor, the position sensor, the current sensors, and any other sensors we are trying to use for the controls, we need to have redundancy in that. High speed fail-tolerant communication hardware between various ECUs. Remember, there are multiple ECUs communicating with each other for the whole system to work. So we need a high tolerance system, fail tolerant, so that the communication hardware is good and we are able to communicate between ECUs too. So that is a very key area, and it is a highly developing area in automotive. Moreover, going to EMB has a specific advantage, especially when the automotive is going towards electrical vehicles, and that is using high voltage chipsets. To take the full advantage of the advanced vehicle power architecture, as you guys all know, that with electric vehicle, the voltage level has bumped up, and we can take the advantage of using that high voltage in our high voltage chipset development and use that for EMB. So it need not be a low voltage system. It can go up to like 48 volts kind of system, but we can take advantages of such architecture now. Now, high redundancy in sensors, which I brought about, and power chips and microcontrollers, which is used, increases the cost. So it is very key that in order to provide a viable solution for the market, we need to have smart solutions for the redundancies. Thereby, we are not increasing the cost, but we are able to manage redundancy by keeping the cost at the right ratio so that we can actually sell these systems. So that is a key challenge. High redundancy requirements means higher end MCUs are needed for applications. That means we need a better MCUs which can perform at higher rate. Software needs to power to execute new safety functions. So software speed and the redundancy in the dual controllers needs to be evaluated so that we can run higher, faster diagnostics and higher safety functions such that it can not only provide the amount of safety required and mechanism required to know the issues as well as provide diagnostics. And also, we also need software to be performing without any throughput issues. So we need higher end MCUs for that. High degree of availability of the complete system is required. Therefore, since there's no mechanical feedback in such systems. So for this EMB to work, we need to make sure that the complete system architecture there's high degree of availability. That means when I say availability is that, say a sensor failure happens, we are not bringing down the system. We are still performing with full performance after a single point failures. So we need to understand how well we can provide the performance of the system even after failures. How well can the architecture provide full performance even after a single point failures? Now we are even talking about dual point and triple point failures to make sure that there is adequate performance levels in these actuators so that systems can be brought to the safe place or safe zone or safe area, what we call in industry, when even after a failure happens. So high degree of availability in such architectures are key. So these are design constraints, are design decisions we need to make when we develop these systems. Another area we are keenly looking at is the software systemic failures. That means a systemic failure is key in when we analyze safety now, because a systemic failure can bring down with one fault, system can bring down the whole other systems too. So such as erroneous MCU behavior needs to be addressed, and such fault mitigation in the total system failure, even with redundancy, should be addressed and make sure that such systemic failures are addressed before the design. Thereby, in production, there is no such issues, and the user doesn't have to have a systemic failure at all. Such key areas have to be understood, need to be root caused, need to be developed such that systemic failures are avoided, or we have a plan, even if the systemic failure happens, that we provide adequate power to the system so that the system can be brought to the safe zone. Now, so my last slide, why HL? Why we should go with HL for EMB? What is our expertise? And this really lies with what we do today as a core. HL is trying to are the first expertise in first fully redundant production steering system. We have developed the first productionized fully redundant architecture for steering systems, which gives us the biggest background or biggest base to go and develop such highly redundant system and how to make it practically possible for productionizing, and how to make sure the cost is not high, but still provide the full safety. So we have a good expertise in that area because we have developed the steering system with fully redundant architecture. So we are taking that, and that is a huge background we have to make sure we are developing the right EMB architecture. Expertise in fully redundant IPMSM and PMSM motor drive. We are experts in motor drive architectures and give us full redundancy. That means even after a sensor failures, we are able, even after a single point failure in any of our architecture, which includes sensor, power electronics, and motors, we are able to provide full architecture, full performance. So we have systems already developed which can provide a full performance even after a first point failure. We are also developing systems which can provide adequate performance even after dual or triple point failures. Expert in doing this needs, in order to develop such architectures, we are expert in doing such safety analysis for such complex systems. That is a huge area of technical development where we analyze the safety even before the designing the architecture. How to analyze that safety for such complex system to understand the single, dual, and latent point failures. We are expert in that, and that's how we developed our first productionized steering systems. So we are very good at that aspect. Experting in developing advanced motor controls, including systems with low torque with active cancellation. This is a key in areas like steering and brakes, where we can still use IPMSM drive systems. As you all know, IPMSM drive systems inherently has a lot of torque ripples, and the performance are bad because they use less rare earth magnet, and thereby we can reduce the cost. But how do I productionize so that the performance is good? We have active torque cancellation techniques, which we already developed and applied in steering systems, which we are also trying to incorporate in EMB, thereby providing a very good performing systems and very good low torque ripple systems, even with IPMSM drive systems. Thereby, we are reducing the cost in the motor because it has less dependency on rare earth materials, and also, but still performance is not mitigated. Performance is not reduced. We are still having high performance with such active cancellation technique. We have also demonstrated, especially for EMB, how to have high bandwidth force control system, especially in the areas of ABS, and improving much. It's actually better than the present hydraulics ABS, how we can improve because of a high bandwidth force control mechanism and high response in force control. So all these aspects, which are key for a good architecture for EMB, we are expertise in that, and we have actually shown the solutions even in steering systems, which we are taking over towards EMB to provide a better performing, safer, and highly performing systems for meeting all the OEM's requirements and needs for a good performing EMB architecture. Thank you. I thank all the people for our presentation, and I really thank you for listening to this. Thanks a lot.
예, 이번 마지막 영상을 끝으로 기술 세션은 준비된 영상이 모두 마무리되었습니다. 지금부터는 사전에 말씀드린 Q&A 시간으로 영상 시청 중 참석자분들께서 올려주신 질문을 현재 HL만도 헤드쿼터에서 EMB 하드웨어 개발과 소프트웨어 개발을 맡고 있는 공영 팀장님과 김용길 팀장님이 답변을 해주시겠습니다. 우선 첫 번째 질문을 드리겠습니다. 아무래도 처음 소개되는 제품인 만큼 질문이 좀 광범위한 내용을 담는 질문인 것 같은데요. 금일 소개된 EMB 시스템은 운전자나 차량 측면에서 어떤 혜택을 주는 제품인지 설명을 해주시면 감사하겠습니다.
이 부분에 대해서는 제가 좀 답변을 드리겠습니다. 앞서 첫 번째 세션에서 미국의 제프 폰티어스가 EMB의 어드밴티지에 대한 소개가 있었습니다. 소비자나 운전자 측면에서 부연 설명을 해서 좀 드리자면, 그동안 제동 쪽에 있는 신제품, 신기술이 적용된 제품이 있었음에도 불구하고 특히 운전자, 엔드 유저 입장에서는 편의성을 향상시킨 EPB, 일렉트릭 파킹 브레이크를 제외하고 일반적인 주행 및 제동 조건에서 신제품이 적용되었다는 것을 엔드 유저, 운전자가 책임하기에는 좀 어려움이 있었을 것입니다. 차량 주행 안정성을 향상시키기 위한 ABS, TCS, ESC 등, 그다음에 제동거리 단축 및 사고 예방을 위한 AEB 기능이라든가, 그다음에 제동 성능을 향상시킨 AMS 성능을 높인 일반적인 주행이나 제동 조건이 아닌 불안정한 제동 조건에서 동작하기 때문입니다. 반면에 EMB 시스템은 기존 제동 신제품과 다르게 소비자 및 운전자에게 다음과 같은 혜택을 줄 수 있을 것이라 생각됩니다. 첫째, 소비자에게 차량 유지 비용을 절감시킬 수 있을 것입니다. 기존 유압 브레이크 시스템의 경우 초기 응답성 때문에 로드래그를 구현하기에는 많은 어려움이 있었으며 브레이크 오일 등을 주기적으로 교체가 필요하고, EMB 시스템은 제로 드래그 구현 및 회생 제동을 최적화하여 연비 및 전비를 향상시킬 수 있고, 브레이크 오일 교환이 없을 뿐만 아니라 패드 교환 지기를 향상시킬 수 있는 장점 등이 있습니다. 그다음에 두 번째로는 일반적인 주행, 제동 조건에서 EMB 시스템은 운전자의 의지대로 제동을 가능케 한다는 것입니다. EMB 시스템은 브레이크 페달과 파운데이션 브레이크의 완벽한 분리를 통해 운전자의 의지를 판단하고 그에 맞게 알맞은 제동을 구현하여 운전자에게 심리적인 안정감을 더 줄 수 있을 거라고 생각됩니다. 마지막으로 기존 제동 신제품과 마찬가지로 엔드 유저가 체감하기는 어렵겠지만 불안정한 조건에서 좀 더 나은 제동 안정성을 확보할 수 있을 것입니다. 기존 유압 브레이크 시스템 대비 빠른 모터 동작으로 제동 거리를 단축시킬 수 있으며 각각의 휠에 대해서 독립 제어를 통해 최적의 제동 성능을 구현할 수 있을 것입니다.
예, 설명 감사드립니다. 다음 질문으로 넘어가겠습니다. 아무래도 브레이크 바이 와이어 시스템은 자율주행 차량에 적용되는 만큼 안전에 대한 관심이 많은 제품이라고 생각되지는데요. EMB 시스템에서 한 개의 제품이 고장날 경우 어떤 안정성을 유지하는지, 특히나 그 구동륜에 속하는 프론트 휠이 고장났을 경우를 중심으로 좀 설명을 해주시면 감사하겠습니다.
네, 안녕하세요. EMB 소프트 개발을 담당하고 있는 김윤길 책임입니다. 기존의 시스템하고 비교했을 때 기존 유압 제동 시스템의 경우 한 개의 전륜이 고장 발생한 경우에는 일반적으로 능동적인 제어 모드에서 수동 제어 모드로 전환이 되게 됩니다. 예를 들면 전륜 휠에 하드웨어 밸브가 고장이 감지가 되면 일반 ABS나 ESC가 없는 CBS 제어 모드로 전환이 됩니다. 고장 발생한 경우 운전자가 제동을 하면 좌우 전륜의 제동력 차이에 의해서 직진 제동이 안 됩니다. 한쪽으로 선회하면서 제동이 되게 되며 운전자의 제동력이 커지면 커질수록 이때의 그 선회력은 증가합니다. 만약 운전자의 급작스러운 제동의 경우에는 차선을 벗어나서 사고로 이어질 수 있는 경우도 발생 가능합니다. EMB 시스템에서는 전륜 한 개의 고장이 발생하였을 때 나머지 세 바퀴의 제동력 분배를 통하여 제동하게 됩니다. 좀 더 상세하게 고장에 대한 제동력이 부족한 부분에 대해서 제동력을 높여주고 좌우 비대칭에 의해서 발생한 요 모멘트를 감소시키는 방향으로 제동력을 분배하게 됩니다. 또한 시스템의 확장 관점에서는 요 모멘트 감소를 위한 스티어링 시스템과의 협조 제어를 통해서 차량의 안정성을 추가로 확보할 수도 있습니다. EMB를 적용했을 때 추가적인 장점으로 각 바퀴의 제동력이 각 휠별로 통신에 의해서 이루어지기 때문에 새로운 정책의 적용이나 시스템의 구성이 변경되었을 때 기존 시스템 대비 좀 더 유연한 변경이 가능한 점입니다.
네, 설명 감사드립니다. EMB가 확실히 다른 브레이크 제품에 비해서는 안전한 제품인 것 같은 것을 잘 설명해 주신 것 같습니다. 세 번째 질문으로 넘어가겠습니다. 저희 회사에서도 요즘에 환경 관점이나 ESG 경영에 대해서 굉장히 중점적으로 추진하고 있는 부분이 있는데요. EMB 시스템이 환경, 특히 ESG 측면에서 어떤 기여를 하시리라 예측하시나요? 그 부분에 대해서 좀 설명해 주시면 감사하겠습니다.
예, EMB 앞서 간략하게 설명을 드렸지만 ESG 측면에서 특히 환경 부분에 EMB 시스템이 기여를 할 수 있다고 생각됩니다. EMB 시스템은 앞서 설명드린 바와 같이 제동 제품에서 연비 및 전비에 영향을 주는 드래그를 제로화하여 내연기관 차량의 연비를 향상시켜 탄소 발생을 줄이고 특히 전기차의 경우에는 제로 드래그 구현 외에도 최적의 회생제동 성능 구현을 통해 전기차의 전비 향상 및 제동 시 발생하는 마찰재 분진 발생량을 감소시킬 수 있을 것입니다. 마지막으로 EMB는 브레이크 오일을 사용하지 않는 친환경 브레이크라고 생각합니다. 이러한 부분들이 ESG 측면에서 특히 환경 부분에서 기여를 하리라고 생각됩니다.
예, EMB가 안전, 기능 부분 외에도 환경적인 측면에도 상당히 많은 부분에 대한 기여를 할 것이라고 생각되어집니다. 네 번째 질문으로 넘어가서 EMB는 하드웨어적인 면도 중요하지만 제어적인 측면에서 기존 제품에 비해 추가적으로 제공되거나 가지고 있는 장점이 많다고 알고 있습니다. 이런 부분에 대해서 어떤 내용이 있는지 설명해 주시면 감사하겠습니다.
예, EMB 시스템이 기존 유압 제동 시스템이 갖고 있는 기능을 기본적으로는 다 가지고 있습니다. 거기서 추가적으로 이제 신규 제품이기 때문에 추가되는 적용이 더해지게 됩니다. 과거 유압 필리퍼 대비 피스톤의 위치 제어 측면에서 유리해지게 되는데요. EMB에 들어가 있는 모터의 구동 방향에 따라서 피스톤을 밀 수도 있고 옆으로 당길 수도 있습니다. 그런 제어가 가능하고 정밀 위치 제어가 가능합니다. 따라서 기존 유압 시스템 대비 크게는 두 가지 기능을 더 가질 수 있습니다. 패드의 마모를 측정하는 기능이 추가됩니다. 이런 기능의 장점으로선 마모 수준을 미리 확인이 가능하고 브레이크 패드가 마모되기 전에 서비스를 미리 받을 수 있습니다. 그리고 향후에는 자율주행이나 차량 공유가 계속 확대되고 있는데요. 이런 경우에는 더 유용한 기능이 될 수 있습니다. 또한 피스톤의 정밀한 위치 제어가 가능하기 때문에 드래그 양을 저감시킬 수 있습니다. 드래그 양하고 제어의 응답성은 트레이드오프 관계이긴 한데요. 차량의 주행 상태라든지 조건에 따라서 이 드래그 양을 조절할 수 있습니다. 이에 대한 부가적인 장점으로 연비 향상이라든지 브레이크 분진에 대한 환경 문제도 개선이 도움이 됩니다. 페달과 제어기가 분리되기 때문에 ABS나 ESC 제어 시에 페달의 이질감을 없앨 수도 있고요. 그리고 페달 움직임에 따라서 제동력이 가감이 가능하기 때문에 소프트웨어적인 기법을 통해서 이것도 튜닝이 가능해집니다. 앞서서 설명을 했지만 액추에이터의 고장이 발생했을 때 효과적으로 제동이 가능하며 제동 시스템이 구성이 변경되더라도 현재보다 유연한 대응이 가능합니다. 예를 들면 전류는 유압, 후류는 EMB 시스템, 혹은 3축 차량 시스템, 그리고 대형 트레일러가 장착되는 경우에도 현재보다 빠른 적용이 가능합니다.
예, 제어적인 기능의 장점도 상당히 많은 시스템이라고 생각되어집니다. 아무래도 지금 질문 올라오는 내용을 보면 이 부분에 대한 기능적인 부분이나 환경적인 부분에 대해서도 관심이 많지만 역시 언제 시장이 도입이 되고 그런 부분에 대해서 어떤 문제가 있거나 허들이 있는지에 대해서 굉장히 관심이 많은 것 같습니다. 그래서 다섯 번째 질문으로는 EMB 시스템이 언제 자동차 시장에 도입이 될 것 같고 또한 그를 위해서는 어떤 허들이 제거되어야 되는지에 대해서 좀 설명을 해주시면 좋을 것 같습니다.
예, 그 부분에서는 제가 설명을 먼저 드리겠습니다. EMB 시스템이 자동차 시장에 도입하기 위해서는 자동차 카메이커의 역할과 저희와 같은 티어원 업체 역할에 따라 크게 두 가지의 허들이 있다고 생각됩니다. 첫 번째는 카메이커의 역할인데요. 기존 유압 브레이크 시스템에서 브레이크 와이어를 위한 새로운 아키텍처를 구성해야 된다는 것입니다. 현재는 북미 카메이커를 중심으로 BBW 아키텍처를 스터디하고 검토하고 있으나 현재 각 자동차 회사마다 차이가 있을 뿐만 아니라 지속적으로 지금 변경되고 있습니다. BBW 아키텍처가 지속적으로 변경되고 있다 보니 저희 같은 티어원 업체에서는 EMB 시스템 개발 방향을 수립하는데 약간의 어려움이 있습니다. 그래서 저희 같은 경우는 BBW 아키텍처 영향이 좀 적은 각 휠에 장착되는 EMB 하드웨어 및 소프트웨어의 개발에 집중을 하고 각 OEM이 BBW 아키텍처를 구성하는데 많은 기여를 하고 있습니다. 둘째로는 저희 같은 이제 티어 1 업체가 담당하는 부분이 되겠습니다. 그 부분은 EMB 시스템 가격입니다. 아직은 EMB 시스템이 시장 도입기라 EMB 시스템 가격이 기존 시스템 대비 가격이 많이 비쌀 수밖에 없는 현실입니다. 하지만 현재 저희도 EMB 시스템 가격을 낮추기 위해 많은 노력을 기울이고 있으며 이 가격적인 부분은 시간이 지남에 따라 점차 EMB의 물량이 증가가 된다면 기존 시스템보다 EMB 시스템이 충분히 경쟁력을 갖출 수 있다고 생각됩니다. 시장 도입 시기에 대해서는 현재 전통적인 카 메이커는 북미 고객 중심으로 2026년에 전류는 유압, 후류는 EMB인 하이브리드 시스템이 먼저 출시될 것으로 예상하고 있으며 포힐, 네 바퀴에 모두 EMB가 적용되는 풀 시스템 EMB의 경우에는 대략 한 2027년이면 출시될 것으로 예상되고 있습니다. 하지만 반면 기존 OEM이 아닌 NTO의 경우에는 좀 더 빠른 시기에 출시할 가능성도 현재는 배제할 수는 없을 것 같습니다.
예, 감사합니다. 추가적으로 만도에서는 올해 새로운 해에 꼭 시장에 진출하려고 노력을 하고 있고요. 이 부분에 대해서 저희가 세계 최초로 양산하는 그런 좋은 기회가 있었으면 하는 바람으로 지금 개발을 진행하고 있습니다. 이번 질문을 마지막으로 저에게 주어진 시간이 모두 다 된 것으로 보입니다. 저희가 예상했던 분들보다 많은 분들이 참석해 주신 부분으로 확인을 했는데요. 참석자분들의 적극적인 참여로 저희가 준비한 행사가 더욱 알차고 빛난 시간이 된 것이 아니었나 싶습니다. 오프닝 시 말씀드렸던 바와 같이 본 행사 중 답변드리지 못했던 질문에 대해서는 저희가 행사 후 확인해서 개별적으로 대답을 드리겠으며 혹시라도 이번 세션 중에 질문을 하지 못하신 부분이 있으면 저희가 채팅창에 저희들의 이메일 어드레스를 알려드릴 테니까 그 부분으로 질문을 주시면 저희가 답변을 드릴 수 있도록 준비하도록 하겠습니다. 예, 감사드리고 마지막으로 새롭게 시작하는 한 해 참석자분들께 행운이 가득하시기를 바라며 본 행사를 마치도록 하겠습니다. 감사합니다.